This is the Calculus Pre-Lecture Series. I'm Brandon Ashley, and this video is on the integral test. So we want to say something about the convergence or divergence of a series, and one way to do this is to represent a series with areas of rectangles which correspond to the area under a curve. So for example, we might look at the series n equals 1 to infinity, 1 over n, with areas of rectangles corresponding to the function f of x equals 1 over x. And if we do this, it's going to look something like this. We'll get a rectangle of area 1, and then a rectangle of area 1/2, 1/3, and so on. Like this. And we notice that the areas of the rectangles actually overestimate the area under the curve. So I get these extra chunks of area in my rectangles. And what this means mathematically is that I can write the integral from 1 to infinity of 1 over x dx is going to be less than or equal to my series. So if I add up these areas. And this is great because we know how to calculate this integral, so we might as well do it. This is going to be the limit, put an equals, as b goes to infinity of the integral from 1 to b of 1 over x dx. But this is just the limit as b goes to infinity of ln of x evaluated from 1 to b, which is the limit as b goes to infinity of natural log b minus natural log of 1. But natural log of 1 is just 0, so that term goes away, and we're left with the limit as b goes to infinity of natural log b, and that's just infinity. So we get that this integral goes to infinity, and our sum is going to be bigger than infinity, which means that it has to go to infinity as well. And this means the series diverges. And similarly, we can do this with the series n equals 2 to infinity of 1 over n squared, and the associated function would be 1 over x squared this time. And if we write in our rectangles, we would have over here at 2, going back to 1, this rectangle, and then from 3, 1 there, and 1 in here, and so on. And we notice that each one of these rectangles is an underestimate, and so we would then write that the series n equals 2 to infinity of 1 over n squared is going to be less than or equal to the integral from 1 to infinity of 1 over x squared dx. And again, evaluating this, we're going to get that the integral from 1 to infinity of 1 over x squared dx is equal to the limit as b goes to infinity of the integral from 1 to b, 1 over x squared dx. And you can check that this is just going to be 1. So we get this integral is just 1, which tells us our series converges, and it's going to converge to a value less than 1. So we'll even write the series from n equals 2 to infinity, 1 over n squared, is less than or equal to 1. So what this is telling us is if we have a series sum a sub n, and we can find a function such that a sub n is equal to f sub n, then if f of x is positive, decreasing, and continuous, then the integral, I'll just write integral from 1 to infinity of f of x dx, and the series a sub n either both converge or both diverge. And that is exactly the integral test.